Welcome, future scientists. Today, we're about to embark on an amazing journey into the tiniest world you can imagine. We're diving into the world of atoms, the super tiny building blocks that make up everything around us, from the air we breathe to the shoes on your feet. Imagine atoms as the Lego bricks of the universe. Just like you can build anything with Lego, atoms can be combined in countless ways to create all the different things in our world. Everything you see, touch, or breathe is made of these tiny particles. Even things that look totally different, like a rock and a cloud, are made from atoms arranged in unique ways. Take a simple glass of water. It might look ordinary, but it's actually made of millions and millions of molecules. And each molecule is built from atoms, specifically 2 hydrogens and 1 oxygen, which we call H2O. If you change the atoms or the way they're connected, you can create something completely new. That's the magic of chemistry, mixing and matching atoms to make new substances. Understanding atoms helps us solve mysteries, like why ice floats on water, how plants grow tall and green, or even why we need air to breathe. Atoms are the foundation of all matter, and learning about them lets us invent new materials, discover life-saving medicines, and even build rockets to explore outer space. By studying atoms, you're learning the language of the universe, the code that explains how everything works, from the tiniest bug to the biggest planet. So get ready to shrink down, use your imagination, and explore this invisible, incredible world that's hidden all around us. Welcome to the atomic party, where science gets super small and the possibilities are endless. The idea of atoms began over 2,000 years ago with Democritus, a Greek philosopher who imagined that if you kept cutting matter into smaller and smaller pieces, you would eventually reach a piece so tiny it could not be divided any further. He called this fundamental building block atomos, meaning indivisible. Although Democritus had no way to prove his idea, his vision planted the seed for a concept that would shape science for centuries to come. For centuries, the atom remained a philosophical idea, debated by thinkers but lacking evidence. It wasn't until the early 1800s that John Dalton, an English scientist, revived the concept. Through careful experiments, Dalton noticed that elements always combined in fixed, simple ratios to form compounds. This led him to propose his atomic theory, suggesting that each element is made of its own unique kind of atom, and that these atoms combine in predictable ways. Dalton pictured atoms as solid, indestructible spheres, tiny, hard particles that made up everything around us. His model was simple, but it provided a foundation for future discoveries. Yet, as science advanced, new experiments began to reveal that atoms were far more complex than anyone had imagined. In 1897, J.J. Thomson, working with cathode ray tubes, discovered the electron, a tiny, negatively charged particle inside the atom. This was the first evidence that atoms were not solid and indivisible, but contained even smaller parts. To explain his findings, Thomson proposed the plum pudding model. He imagined the atom as a sphere of positive charge, with negatively charged electrons scattered throughout it, like raisins in a pudding. This model was a big step forward, but it wouldn't last long. Then, in 1909, Ernest Rutherford and his team performed the famous gold foil experiment. They fired tiny particles at a thin sheet of gold and observed how some bounced back unexpectedly. Rutherford realized that most of the atom is empty space, but at its center lies a tiny, dense, positively charged core, the nucleus, where nearly all the atom's mass is concentrated. This discovery completely changed our understanding of atomic structure. This led to the nuclear model of the atom, with electrons orbiting around a central nucleus, much like planets around the sun. The atom was no longer a simple sphere, but a miniature solar system with its own mysteries. The atom was no longer indivisible, but a complex structure with a rich history of discovery. Each new experiment revealed more about the hidden world within matter, inspiring generations of scientists to keep searching for answers. From ancient ideas to modern science, our understanding of atoms keeps evolving. The journey from Democritus's imagination to today's high-tech laboratories shows how curiosity and experimentation drive progress. Each discovery brought us closer to the true structure of matter, revealing new layers of complexity and wonder. The story of the atom is a testament to human ingenuity and the power of asking questions. And the journey isn't over yet. As we continue to explore, who knows what secrets the atom will reveal next. Let's meet the atomic family protons, neutrons, and electrons. Protons are positively charged and define the element. 1 proton means hydrogen, 6 means carbon. Neutrons have no charge and help hold the nucleus together, acting as atomic glue. Atoms of the same element can have different numbers of neutrons. These are called isotopes. Electrons are tiny, negatively charged, and zip around the nucleus in energy levels. It's the electrons, especially those on the outside, that create chemical bonds and reactions. In a neutral atom, the number of protons equals the number of electrons, balancing the charge. These three particles work together to form every atom in the universe. Mastering them is your first step to understanding chemistry. So, how are these particles arranged? Let's take a closer look at the incredible structure of the atom, the building block of all matter around us. Picture an atom like a mini solar system. At its heart is the nucleus, a dense center packed tightly with protons and neutrons. This tiny core is unimaginably small, yet it contains almost all the atom's mass. Almost all the atom's mass is in the nucleus, held together by the strong nuclear force, one of the most powerful forces in nature. Without this force, the nucleus would simply fly apart. Electrons, which are much lighter, move rapidly in a vast space around the nucleus, forming what we call an electron cloud. This cloud isn't a solid shell, but a region where electrons are likely to be found at any moment. We can't pinpoint exactly where an electron is at any given time, but we can predict the regions where it's most likely to be. These regions are based on probability, not certainty. These regions are called energy levels or shells, and each shell can hold only a certain number of electrons. The arrangement of electrons in these shells determines how atoms interact with each other. The attraction between the positively charged nucleus and the negatively charged electrons keeps the atom stable, preventing the electrons from drifting away. Most of an atom is actually empty space. If the nucleus were the size of a marble, the nearest electron would be several football fields away. The solid feel of objects comes from the interactions between electron clouds. When you touch something, it's really the repulsion between your electrons and the object's electrons that you're feeling. This elegant structure is what makes every atom unique, giving rise to the incredible diversity of matter in our universe. Now let's look at the atom's blueprint. The atomic number tells us how many protons are in the nucleus. This defines the element. The periodic table is organized by atomic number. The mass number is the total of protons plus neutrons. Electrons are so light, their mass isn't counted. In a neutral atom, electrons equal protons, balancing the charge. Atoms can gain or lose electrons to become ions, but the number of protons never changes. The nucleus gives the atom its identity and mass. The electrons determine how it interacts. This structure repeats for every element, from hydrogen to the heaviest metals. Understanding this blueprint is the key to predicting how atoms behave. Let's sum up the essentials. Atoms are the basic building blocks of all matter. They're made of protons, positive, neutrons, neutral, and electrons, negative. Protons and neutrons are in the nucleus. Electrons orbit outside in shells. The atomic number, protons, defines the element. The atom's mass comes from protons and neutrons. Atoms are mostly empty space, with electrons forming a cloud around the nucleus. In a neutral atom, protons and electrons are balanced. This balance is crucial for stability and chemical reactions. Master these points, and you've unlocked the basics of atomic science. Ready to test your knowledge? Here are the key questions. What is an atom, and why is it the basic building block of matter? Name the three main subatomic particles. What are the charges of protons, neutrons, and electrons? Where are protons and neutrons found? What is this part called? Where are electrons located? What makes one element different from another? What does the atomic number tell us? Why is an atom electrically neutral? Which particles account for almost all of an atom's mass?